Okay. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum, everyone. This session is going to be as following this notebooks. It has been put into chunks, so it's not going to be boring for the audience. Although this topic is really can't be covered in one webinar or even training course. It needs a lot of time and dedication, but it will pay off for those who are gonna get engaged in this topic, hopefully by the end of this eye-opening webinar. So to start with, let me just say good afternoon, my time, and good perspective time for all of you. And my time and respective time. Okay. This is the agenda of the webinar, as we can see here. Each notebook stands for one of the topics of this agenda. We will go through this time series, Frontier, Applicability and Potential for Oil and Gas Industry. And we will just shed some lights on very few applications in upstream oil and gas. So we'll talk about introductory part, and we will see the analysis for time series. And this will be followed by detailed forecasting models. But we will see also the applicability and uses both in statistical and machine learning, statistical and machine learning models. And we will come through a very, very important concept, which is prediction intervals. That is a very important step, I believe. Most of the users are not really taken care of. This is to quantify the uncertainty associated with our models and our model results. So we'll have as well a talk about the difference between the confidence interval, the statistical confidence interval. Most of the audience, I believe, know what is confidence interval, and compare it with this new concept in application. It's not new in theory, but it's new in its application, conformal prediction interval. Having said so, we will also see some examples regarding multivariate time series, both forecast and clustering. And we will have this ending note and wrap up this webinar. So all these notebooks are ready because they take time. So I just made them ready. So we won't spend time while processing the codes and running them. So to start with, this time absolute, as Sir Isaac Newton has stated in his view, like consistent unchanging progression of time. So we try here to express this view in this space from 0 to 100. And if time is absolute, running this code, we will get something like this. So this is time. Albert Einstein came later, and the theory of relativity is telling that where time's passage varies depending on relative motion and gravitational field. So if we try to code and plot this concept just to have an idea how would time look like in this concept, we will put a code like this, and time will look like this. So along this space, the time will have different values depend on where this time occurs. Not only scientists, even there are so many different concepts, we would say, like literary concepts, like Ray Cummings in his novel The Time Professor, 1921, he put this very nice quote, you know, time is what keeps everything from happening at once. And we can see this quote presented by this plot over here. So we can combine all and we can see different concepts over here. We could say one of these is actually the concept of time, or maybe none of them. Okay, now we go to our second notebook. So this notebook is intended to introduce time series. Mathematicians have their views on time series. So the definition of time series in mathematics is a series of data points indexed in time order. So time series is a sequence at successive equally spaced points in time. And time series is not something that is strange. No, we face and we see time series in our daily life every day in different ways. We choose this example of a step counter, like everyone who has a smartphone can relate this. So we assume that that we have a student who goes to the university and come back twice. So he went to the university and he come back. So he go through this university distance 2 times a day. He goes to the library from the university sometimes, and sometimes he goes to the library from home, and he just did some exercise in weekends. So we define a function for that, and we name the function like steps for distance, as you can see here. So we calculate number of steps for a given distance, and we create a data frame for a given date, and this function returns the date time index, which is a sequence of date time objects, obviously, and the data frame with steps will add a new column and keeps the number of steps. So this is just to make it like easy for those who are not really familiar with Python and coding. It's just simple logic, and it needs just some practice. And nowadays it's easy to find like even artificial intelligence assistance in doing coding. So the important thing is to know what to code actually. So we just generate this. We put some random choices for going to university or library or doing exercise and whatnot. And we kept all this series, and now we will just plot it. So we filtered our data frame for the first week of January, and this is actually the plot of the number of steps versus time. This is one way of looking at it. We can as well have it in this plot form. So we can see there is nothing this day as well. Here there is almost 5,000 steps, and it keeps going up sometimes, increase a little bit sometimes. If we have a look on the first month, we will get this shape. So this is the daily steps in January 2022, and we can see it by quarters. So this is the first quarter from January to March, and as you can see, this shape is start to develop and get some complex patterns. So, and this is the whole year for 2022. So if we kept tracking for the whole year, maybe this is something that we can end up with. Okay, so can anyone relate this concept to his field, especially in oil and gas? If so, please drop a message in the chat. Okay. The next message is we can relate time series even to like unexpected fields. Like if we have something like this, on a skull, which would be very interesting for archaeologists maybe, or history people. Can we see this skull information in different format? Answer is yes. So we can change the way of perceiving the information. So we just import the necessary libraries. We set our threshold. We played a little bit in the pixels and the appearance of this image. And we set a centroid in this skull, and we just calculate the outer contour, the circumference of this skull. So we run this code, and we get the distances from our centroid point, and we have this distance 1, distance 2, distance 4, and they are successive, and they are similar in nature for time. So if we plot this, you can see how it works. So this white line actually calculates the number of pixels from this point to the outer contour of this image. So this image, applying this concept on it, can be now seen as this plot. And this opened a new whole frontier of processing the image, being able to convert the information from image to series. So, and if we just flip a little bit, this will remind us, especially in upstream, for instance, the wireline logs, for example. So the credit for this skull idea goes to Professor Abdullah Muin from University of New Mexico. I just, it happened that I saw this YouTube video, as you can see here, and I was able to just make it the way you have seen it earlier. Okay, by this we end this notebook. Let's go to the next one. So now we can relate the previous notebook to this wireline geophysical survey logs, which can be also easily converted into time series domain. And let's now talk about one of the chronic problems, for example, the low resistivity, low contrast Bayes zone. And I would refer to this work. You can get the source over here. So you can see this is a water zone. This is oil and gas, and this is oil. And it's coming from different intervals of the well, but it was put this way just to draw the attention that this resistivity of water is much higher than resistivity of oil, which is a contradiction to physics. And it happens due to different reasons. So many reasons can lead to this phenomena. But the impact is, it actually costs a lot. Even from the name, you can just figure out it's a missed Bayes zone. So this can be solved by different techniques. One of them is pattern recognition. So we'll see here, like this is Grand Slam, wireline logging suite. So we have this training set. We import it using the right libraries, and we index it. We set it for the view to just look like exactly how people in the industry set the view for this type of work. We gave like some standard colors, and this is what we came up with. Gamma ray, and here it is overscaled, so it shoots over and it's higher than 150. And this is our deep resistivity, LLD. So we can move from log to pattern, and we can use matrix profiling concept for pattern recognition, which was introduced by Dr. Main and his colleague few years back. So what is actually matrix profiling is we first create matrix from our series so that each matrix would represent a specific segment or window of our time series. In this case, we have chosen like 10 points, 10 readings, 10 time intervals, 10 whatever. Or so we can put and we can test different time windows. And then we profile the matrix. Like we check and see, is it repetitive? Is there a repetition of this window? Are there any segments that repeat over time? If there is a specific trend across these segments, if there is anomalies, like unexpected patterns in some segments. So it simply use so-called similarity measurements, like Euclidean distance. And we break time series into matrix, and so this structured format is easy to be studied, and we can get a result as we will see later in this notebook. So this code will just run this matrix profile using Stambi library, and we have created this data frame to keep the result. And now we can visualize our pattern. So we put some potential windows with different sizes, like 1 week, for instance, or 7 points, 14, 30, and we can put more, but we will get different results as we change the and keep changing the window size. So now we just interested in plotting resistivity and the respective matrix profile for this specific time window. And we will see like the top 5 similar segments, I would say, or patterns, each for 7 window size of 7. So we can see here 1, 2, 3, 4, and 5. And when we change it to 14, we can get 1, 2, 3, 4. And when it is like 30, we end up with only 2 similar patterns. So this is one of the applications that can be carried on time series domain. And this specific problem also can be approached differently with classification techniques. So there is a lot of applications, and that also implies a lot of opportunities. There is another domain of time series, which is a frequency domain. So frequency domain deals with events of time series differently a little bit. So it concentrates on different parameters. We can see some of them later in one of the upcoming notebooks. But it's all about wavelet frequency and stuff. And it is also very common in upstream, like in NMR, nuclear magnetic resonance, and seismic for sure. And this is one of the works that is intended to handle this. We will not go deep into this frequency domain for now, but just to let you know. So this is the end of this notebook. Let's go to the next notebook, which is the main and the major notebook of the day. So it's about time series analysis and forecasting. Okay, this notebook is going to handle like a full workflow, hopefully generic one for sure, but this will give an idea about how to utilize time series. So data pre-processing is for sure a must, and it is essential. So we have to ensure that we are dealing with clean data, free of anomalies, outliers, and no missing values. And we have to put it in a form, such form that is suitable to enable us for further carry the analysis and do the model at the end. So one of the problems that we can face with any type of data for sure is having missing values. And there is a lot of techniques to handle these missing values. The easiest is for sure just drop them and get rid of them and just have peace in mind. But this simplest way might not really work in all the cases. So we can go for forward fill, is where we replace the missing values with the previous values in time series, or we can go for backwards, the other way around. So we replace the missing value with the next value, or we can go for linear interpolation, assuming a relationship between the adjacent points. Or we can train a specific model to predict and fill the missing value based on other observations. So it depends, and it's case by case. Okay, to start, let us just import our libraries. Let us randomly generate like synthetic with trend and seasonality. So those are concepts that we are going to see very soon. And we have added some noise, random noise as well. Some missing values as well, outliers, and we created this DF, this data frame. The other question is how to handle outliers, because they can significantly affect the results of our analysis, first place, and for sure our model result later. Outliers can be detected visually by plotting time series, or we can use statistical techniques like z-score, which will leave these outliers away from the mean, so we can see them again and we can calculate them and we can figure out them. Or we can use rolling statistics like rolling means and standard deviation. And one of the most important techniques is domain knowledge. Sometimes we can see very odd values, but it doesn't necessarily mean that these values are outliers. So once we detected them, we have to handle them, we have to remove them, we have to replace them, and we can use the whole data set after that. So this is how it looks like. How is our synthetic time series data with outliers look like? So we can just say from the first glance that these values are really high. They don't belong to most of the other values. And this one value is quite low as well. And it looks like it's not part of the series. Here comes this concept of exploratory data analysis. So we have to explore to characterize this time series data to uncover the underlying patterns and anomalies and so forth. So visualizing time series itself is a method, as we have seen. This is another view you can see here. The other method is using box plot. So this box plot, as you can see here, encapsulate all the data between these two lines and tells us we have some points up here and we have this point down here, and they are not belong. So again, it's worth mentioning this is not always applicable. You have to use domain knowledge with the data set that you have. So we plot this box plot, and we get some statistics. So now we know that the median, the 50th percentile is 105, this line. The 25th percentile is 98, this one, and the 75th is 111. So our lower bound is almost 80, upper one is 130. So we have like 12 points that considered to be outliers. Okay, so now we know them. Now we have listed them. Now we know when this event took place. We have everything just by applying this technique. The other technique, as said earlier, this histogram as well can convey the same message. This is one point over here, and the rest are here after 140. So if we have significant values that are missed, what should we do? How do we handle missing values? And how do we handle outliers? So there is multiple approaches for this. Deletion is the easiest. Imputation is the one that we have used, actually. So we have used KNN imputation, which replacing missing values with the average of KNN values in the multidimensional space of the data. But there are much more methods that can be used. So model-based imputation, time series imputation, multiple domain-specific imputation. And this is where, again, domain knowledge and expertise come onto the stage. Okay, so we'll start removing our outliers. We impute the missing values, and we compare before and after box plots. So before imputation and after removing outliers, this is how was box plot of our data looks like. But after we replaced with using our imputation method, it is this one. So you can see we have barely 3 points that more than 125 in value. Excuse me. So we can get the interpretation as well. And here again, we test, so no outliers found this time. And the potential values that we have set, the 3 values are here. And this is the comparison with the statistics as well. So in order of removing outliers and imputing missing values, it depends on the nature of the data, and there could be 2 sequences. So we can remove outliers first, and then we do imputation. It has its own pros and cons, and we can do our imputation, and then later we remove whatever being classified as outlier. And again, it is dependent based on the nature of the data and the domain knowledge. So nevertheless, some general guidelines. Understand the nature of the missing data. This is obvious. Analyzing outliers, choosing the right method of imputation, and the goal of the analysis. Why do we carry this analysis? So all these factors will affect the way we handle missing values and outliers and imputation. One more concept is data transformation, normalization, for instance, standardization. This is often required to make the data suitable and to be easily handled. So we have log transform, we have square root and cube root transform, we have box Cox transform, and we have normalization, we have standardization. So I would say let's do some of them together, plot them, and see which is which. So this is our original data. If we go for standardization, so you can see the data now is between 3 and -3 instead of the range that is up to 130. If we go for normalization, this is even a shorter span from 0 to 1, and the rest, varies, depend on the method of transformation. So this is some write-up that's going to be good for you if you have interest and go through later. And there is a comparison as well between the different types and requirements and use cases. So reason of carrying this data transformation, we might need to normalize the scale. We might need to stabilize the variance in the time series. We might need to make our data more normal, Gaussian in nature. So because some algorithms, actually a lot of algorithms in statistics are Gaussian based. Having said that, normal distribution is maybe 90% of the phenomena, events, or whatever in the world. So it is well developed and mature concept upon which a lot of application being built. So sometimes you might need to make your data like more normal, Gaussian-like, to be able to utilize a certain technique or a certain way of analyzing or modeling. So this is one of the important steps to be taken before you go for further steps. Now let's see some simple statistical forecast methods. And we will apply this on our original data. So we are going to see how naive forecast results will look like, how simple and moving averages results as well looks like, and we can compare. So for naive forecast, we just shift by 7 days. We calculate the 7 days lag naive forecast. That means what we will see tomorrow. For example, if we are forecasting to the future, what we will see tomorrow is what we have seen a week ago. And by the way, if we just put like minus over here, we can do reverse forecast to the history. Sometimes we might need to know what had happened, and most of the time we need to know what will happen. So simple average is known, it's the mean value. We just assume whatever is going to take place in the future is just the mean value. Or we can just complicate it a little bit with a window size of 7 days or whatever figure that makes sense, and we keep rolling this window as we forecast in our intended horizon. If we would like to forecast for 1 day or for 1 week or 1 month or 1 year, we can keep following the same, but this will tend to have unstable value when we go far from the end of our series. So let's just see what this code gave after we run, and let's see the plot. So in this plot, we plot the original data with different simple statistical and mathematical forecasting techniques. But let us just compare. If we just plot original versus naive forecast, you can see it's just a shift of the series. So what we will see here at this point where I put my cursor is going to be like the 7th lag value of this blue series. Simple average is this green line. Is really simple. It's just one value. And moving average, I'm afraid it's not really clear over here, but if you can see, so later you can see clearly when you have this notebook. You can notice it's just kind of smoothing the data. You will notice that these spikes are tending to diminish. So this is a zoom in on the same. We just plot this part, and here you can see clearly how they look like, and you can notice the difference in performance between the different forecast methods. So it's now obvious that these methods are not really enough, because we have complexity in the time series itself. So it shows patterns, seasonality, trend, noise, and so on. So the technique to handle start with decomposing. So we decompose our time series, we break it down into its components, which are typically trend, seasonality, and residual or white noise. And we use the appropriate library, and we just run. Then we can see this is our time series named observed. This is the trend component extracted out of this. And you can see the seasonality, this like highly frequent event. And this is the residual that stands for the event that don't really have significant meaning, or might be some outbreaks or outliers or whatever. So the model could be additive and it could be multiplicative. So this is also one of the variables that you have to figure out. You can try both maybe if you don't know, and see and evaluate. Doing this alone is not enough. We have to interpret. So we have to interpret seasonality, and we actually interpret them in a similar way of frequency domain, I would say. So we have to know the frequency, we have to know the amplitude, we have to figure out the phase shift, the envelope, the form, and we could face multiple seasonalities. We can have varying amplitude. So if seasonality is not consistent. So we run this code for seasonality. So you can see the seasonal component. It's clear that there is no seasonality. We can do an interpretation, and we can see the results. So the frequency is approximately 1.1. So whatever happens, it just happens daily, simply. And the amplitude is almost 0.5. So what if we have different windows, we have different periods? So what if we analyze every 7 days, we have different chunks of time, 7 days, 14, 30, 16, 90. So we create them and we keep them, and we extract the seasonal component, and later we plot. So we can end up with a report like this. So whenever we go by 7 days, so the distance between peaks is 1.2. If we increase the window, goes to 1.4, 1.36, 1.6, and it tends to stabilize. But let's see the difference one by one over here. So this is clearly doesn't exhibit any seasonality. This one as well. If we go for 30 days, so we can see it start to go up and down. For 60 days, this is obvious. So every 2 months, something repeats itself. And 90 days is telling, no, this is not right. So this is the normalized transform data. And as you can see, the frequency of seasonality is the same. the amplitude has changed a little bit. So we changed that. We noticed that there is no change between the original data and normalized data. Okay, let's interpret the trend. So this is the trend over here, and so it's mixed. So it's up and down, as we can see, and the residual is just the white noise component, as plotted here. So this leads us to another concept, is stationarity. So which means the mean and variance and autocorrelation of our time series are constant. They are kept with certain values over time, no change. And many forecasting models, as we'll see, like ARIMA, for example, so assumes is stationarity. So non-stationary data, not reliable, so we have to check. We use something called augmented Dickey-Fowler test. And if it is not stationary, we can use a technique that's called differencing. So differencing is just subtracting the previous observation from the current one, and this can help stabilize the mean. We might need to do subtraction with different lags sometime. So this is the test for stationarity, and so really clearly stated that data is stationary, and the distance or difference time series data as well, giving the same result. So it needs to be done before we figure out the auto correlation and partial auto correlation functions. And those simply are just giving the idea about the correlation of a time series with its own lags, you know, like the certain value, this date is correlatable with value 1 day before or 1 month before. And the correlation could be direct between the lagged value and the current one, or it could be partial, going through the other lagged value until it reaches the new value. So plotting them can also provide insights on appropriate model that can be used. Luckily, these things are very easy to perform using advancement of the technology. So having the proper libraries, we can end up with this plot for autocorrelation function partial. So first one is actually the autocorrelation between the point and itself. So this one is not considered, but we can see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 12 lagged values are having a correlation with the value of interest, with the point of interest. So those will somehow come into the formula of the model. And the partial autocorrelation also stated like maybe 3 lagged values or 4 or the 5th lagged value have an impact on the target point that we are testing. So here is some write-up about them. And this is the interpretation. And this is what do they mean for modeling. So we have to select them if we are going to perform like ARIMA model, for example. And luckily we can automatically get these parameters. We can use different techniques, strategies, grid search or random search or cross-validation. And we will end up with the lag order, which is auto regressive term, and differencing degree, 1 lag, 2 lag, 0 lag, and the order of the moving average. So we will keep this data frame, the imputed one. We just save it. We end this session here. And luckily it is just on time. And we go and see the next notebook. So in this notebook, we perform ARIMA model and one other model, as we will see later, and we introduce some new concepts. So we use the same data frame. This is our ARIMA. This is how we auto search our parameters. So we just define this function and let it search within a set span of values for PDQ, and we get the result. So our best order, best score is 202. So understanding these parameters will provide for sure the insights into the nature of the time series and the model to be correct. So 202 in this context means second order autoregressive component with no need for differencing because the time series is stationary. And again, a second order moving average component. And this is simply is the model. So y sub t is equal to mu plus phi 1 y sub t minus 1 plus phi 2 y sub t minus 2 theta 1 and epsilon as an error term. So 2 indicates the AR component, y sub t minus 1, y sub t minus 2, d is 0, q indicates the moving average component will include the 2 previous values of the residual error. So epsilon sub t minus 1 and epsilon sub t minus 2. So let us see how ARIMA model with these defined parameters now will, let's see how it will work. So we we put our best order, we have our model, we call upon our data frame, we put the order as best order that we have got for the entire data set, and we fit our model, we forecast, we do like 90 days forecast. And let us see the plot. So blue is our training data, orange is test data, light orange is forecast of the test, so-called test predictions, and the red one is the future forecast. So is this model good or bad? If we cannot measure and evaluate our model, we won't be able to know. So now we introduce this concept of metrics. This is a very important concept. It varies between error and performance and many more. Just there is a good paper published about this. If you remind me later, I can share it with you. So they are countless, but those are some of the important metrics, like mean absolute error and mean absolute percentage error. And we have some specialized metrics for forecasting, like bias and prediction direction accuracy, and all the definition and the formulas are here, so you can go through later. So we would like now to compute these metrics on two different statistical forecast model, ARIMA and Hall's linear method. And this is how we calculate the metrics. So we just define this metrics. So mean absolute error is just the absolute value of the forecast value minus actual values. And the rest are just the same. So these are just fancy names, but the concept is just straightforward. So we return them and we plot them, and we print them and see. So the same model is now being weighed, being evaluated, so we can tell, like, this model is characterized by mean absolute error of 8.5, RMSE of 10, bias of minus 2.2, and so on and so forth. So let's just apply the same concept on one of the previous models that we have carried, the moving average forecast model. So this one will now give us this shape, but is now characterized by this metrics. The other model is exponential smoothing. So we can have different types of them: simple, double, triple, and simple exponential smoothing is suitable for time series with no trend or seasonality. Double exponential is suitable for time series with trend only, and triple is suitable for both trend and seasonality. So there is no really direct autoregressive or moving average components. However, the absence of the differencing is suggesting that this is like an additive, and the trend of this data might be linear. So we just use this concept. So this is the double exponential smoothing. This is how this is the model simply, and these two lines of code. And here is a plot. Here are the metrics, and it failed. And I think we all just expected this from what we have said. So we have trend and we have seasonality, so it couldn't perform. So you can see now this is the forecast, and it is way off what is the actual test set is. So let's go for triple exponential smoothing, and let us see. I think we have improved a lot here, and this red line is the forecast, and this is a forecast with 90-day out of sample. So this forecast in the future with no any information available except the previous time series. And these are the metrics, as it's obvious. And now we can compare different models, and we can tell this one is better and this one is the best and this one is bad based on tangible values that we have. So we have this plot, and we can tell that ARIMA outperform exponentially smoothing, maybe, or no. Yes, ARIMA is doing better. But if we see here, you can see this forecast predictions are shifted. So this point should be here actually. And this is an exercise I'll leave to you. Just try to play a little bit in this code and try to get a better fit of the model than this one, and rerun, and again see how this comparison of models will change. So one more concept is forecasting horizon, and simply forecasting horizon is if we have this one over here with exponentially smoothing, we can see this model now with better fit, and the horizon is just how far would we like to go in the future. So this one ends over here, and let us quickly try to catch up because I see time has gone beyond our expectation. So in this one, I will just quickly introduce prediction interval concept. So this expresses the uncertainty of prediction by providing set of values possible to be in the predicted outcome, rather than a single point estimate. So it is constructed in such a way it guarantees a predefined level of confidence. So the same previous model, we will see now we have plotted this interval in this very lovely color. And again, if we go for 1 month forecasting 30 days in the future, we can see how the test predictions with conformal prediction intervals look like, and we can plot the months of future forecasting with its respective conformal prediction interval. So our prediction just lies within this 95% prediction interval confidence. So those were just simple statistical forecasting models. We have some advanced machine learning and deep learning models like long short-term memory, which is type of recurrent neural network, and there is more and more. So this new notebook is talking only about conformal prediction and confidence interval, which is which and what is the difference. So the main difference, I would say, in conformal prediction interval, we construct our interval in advance by setting the confidence and assigning percentage for our forecast predicts to take place. Difference from this confidence interval, which is a traditional statistical interval technique. I will just comment on this. So this is a prediction interval of 95% confidence level set beforehand of the forecasting, and this one is the confidence interval that being calculated after the forecasting. If we compare, we will see one of the advantages is this: the conformal prediction interval is more tight, so means more accuracy of the forecast predicts that we have. So this model, of course, could have been better. So you can just play around and try to bring this red line a little bit down and see what you come up with. Notebook number 6 is an application that being carried to forecast future production of one of the wells in Volve oil fields. This is data available from Norwegian company, Equinor. And this is just part of a project. And everything was carried earlier. And this is the data frame that is being used. And these are the parameters like oil production and gas production, water production, and bottom hole pressure, the historic values. And this is physics-based feature selection. We are trying to utilize the concept of productivity index and see if it works to predict the future production. So the concept of conformal prediction as well was incorporated. This is how the model looked like, and this is like 10 months forecast at the end of the life cycle of the field. And we can see this green is the original data. We give this brown to distinguish the test interval. And we can see this is the test interval, and these are the test predictions in blue. And again, we can now see how it performs versus original. So this line in the middle here is the machine learning model. This one is extracted from the simulation model that is provided in the dataset. So just simply this method has outperformed the simulation result with uncertainty quantification over here. And these are the metrics between the forecast data, test data, and the simulated data. And you can see them visually here. So this forecast is outperforming the simulation, traditional simulation techniques. And this forecast is just using 4 parameters, while simulation might need like up to 20, 30 parameters, I would say. If we put this into conformal prediction, so we can have a percentage of 35% is out of bound. So we can see this visually as these points that are lying out of the conformal prediction interval. So we have some of them over here, and we have some of them toward the end of the prediction where the field just not producing anymore. So I hope this is a good example to show you that time series can be very, very useful. We have another example here, and this is clustering. Clustering using dynamic time wrapping. And this is also another technique, a very useful one. We have almost like 20 wells. We compare them to each other. We measure the similarity using dynamic time wrapping technique. I have put some right up over here. You can search for more. So we create a matrix where one sequence is laid out on the x-axis and the other on the y-axis, and then try to find the path through this matrix that minimize the cumulative distance between the two sequences. And one of the good things about this technique, it doesn't matter whether your 2 or 3 or whatever time series that you have, they don't have to be equally in distance or equal to each other. So it ends up with this distance matrix. We can choose our dendrogram based on the features that we would like to test. So we apply this to Norney field, and here you can see the dendrogram of the cumulative DTW, and this is the silhouette scores for the different distances. And if we use only historic production rate, we will be ending up with this. So these are all the wells, and this is the similarity, the distance between each, and we can represent them as you can see here. And we can do again the same clustering based on fluid features, oil, gas, and water, for instance. And we can have new results. So the door is open. The opportunities and potential are huge. And these are the results, as you can see here. So we have done this, and we use domain knowledge to make a hybrid model in which we can be able to specify the design number of clusters. And so this one with 4 clusters will give us this plot, which tells us that this one and this one and this one and this one, these 4 wells are similar to each other, and these are similar, and so on. So one of the potential uses is if we visualize this spatially, so we can have something like this. This is the map, and these are the structural faults. So we specified, for instance, 8 clusters. So if we plot these clusters and show them in this context, this can be very helpful in the iterative nature of reservoir modeling, I would say, the sedimentological model. So this can give you a very quick and effective way of clustering and knowing the relationship between the different wells and how you can relate them and how you can model them and how you can put them with regard to each other. So my end note will be telling you that potential areas are so many: exploration, history, and yet to find resource, production forecast, log analysis, drilling. This is another huge potential. Whether drilling optimization or forecast of drilling parameters beforehand. Reserve and reserve growth, seismic and inversion. This is obvious, especially in frequency domain. Well integrity, equipment, health monitoring, production and optimization, environmental monitoring, pressure transient, and so on and so forth. So thank you very much. We are open